Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about a very important battery topic, battery management system, or BMS for short. So let's dive right into it. Well, first you have to understand what the heck we are talking about. We are talking about a battery. So we have to understand battery itself. Battery is comprised with a group of cells. So your mobile phone does not have a battery. It has a cell, most likely, unless it's an iPhone or some super advanced mobile phone. Most of them generally have one cell. To make a battery, you have to have multiple cells. For example, the 12-volt battery that is in your car or in your UPS or inverters, those are generally 12 volt. Now, are they cell? No, they are a battery because they have 6 cell working in series to give you the power that you need. So we are talking about something like that. Management of a battery, not of a cell, of a battery as a whole. Now, each cell is a chemical system. Now, what does that mean? That simply means it's completely isolated and completely independent. So, let's say one cell starts to misbehaving, others cannot compensate for it. They are like completely isolated. So, if it's like one voltage starts to go down, the whole battery cannot just magically compensate for it. There is no way of doing that. So, it is very critical. You must understand each cell is an independent unit. Now, each cell is also different. Now, people try to bypass this problem because you can understand when you're talking about Tesla Model S, where you have to like hundreds of cells, you will try to make sure each cell is as close to each other as possible. So the only way they can do that is basically manufacture them and deploy them as quickly as possible. Basically, all these cells were made, they are put into one batch. So they will not be like, okay, from this company, I'm buying LG's batteries or Panasonic in the case of Tesla in the early days. I'm just gonna put any Panasonic. They will be like, okay, give me this exact lot. This exact lot will go in this exact car. They will not mix and match lots for this exact reason. So to reduce the probability of mismatching. Now, mismanagement on this sort of scenario, you may think like, hey, what will happen if I mess up one or two cells? Catastrophic damage is a simple answer. So you have to understand mismanagement is ludicrously bad, and whole battery can fail even if one or two starts to misbehave. So it is something that you have to truly manage. It's not a option or luxury or something like that. It's like, yeah, you have to do it. Otherwise, your car will literally stop working in mid road, even though you're technically supposed to have full charge. So this is not an option. This is an absolute necessity. So why do we need this? Well, when I say cell, each cell is different. What do I mean? I mean in three core criteria. Every cell has a C, inherent C, basically their charging rate, how quickly you can charge it without destroying it, damaging it, or harming it. And then we have D, how quickly you can discharge it. These both are generally measured in amperes. So you can have a cell that can like easily, comfortably can handle 1 ampere coming into it. It's like, I'm good, I'm cool. But then you will find the cell next to it would be like, I can easily handle 1.2 amps. I'm okay with 1 amp, but I can handle 1.2. But in D also, it's something similar would happen. It's like, bro, I can dump upwards of 5 amps, no problem. Another cell will like, no, bro. If you ask 5 amp out of me, I'll overheat. So for this reason, these two are different. And then the final thing that actually starts to become more and more worse as time goes along is ampere hour, basically the capacity. So these are not same in the every cell. No matter how good you want to do, how good you're manufacturing, it will never be the same, because electrical chemistry changes over time. Over time, you will always hear things like dendrites or cracks in the basically anode and cathode. Why is that happening? That's happening by the as a byproduct of charging and discharging itself. So will all the cell will have exact same crystallization, exact same shattering of the anode and cathode? No, hell no. So consequence would be, in the beginning it will be like barely any difference, but after 10 days, yeah, there will be some difference. After, let's say, 1 year, yeah, your cells are completely different from each other, even though they literally at the day one they had no issue, but over time they will start to drift apart. Now this drifting apart over time causes what we call feedback loop. So you can have something like this. You have a cell that has like way too a cell that discharges way too quickly. Consequence of that will be there will be a lot of wasted power. So once you went into charging the cell that was like very least drained, it will charge up quickly, and consequence of that would be your cell will stop charging because the voltage reached too high. So it will like, bro, I think the cell is charged, and you have uncharged it. So basically some batteries will permanently end up in a scenario where they're always undercharged, always under current, always in those sort of scenarios. So this will be really bad, and it will keep feedbacking. If you can remove the cell, let's say even if there is a cell that does not have too much capacity, and you use it as a cell, it's like just you as a cell, I want to use it. How long will that last? Very long time, very long time. But you put them in a battery where they have to constantly handle undercurrent or overcurrent, yeah, they're gonna give out in few months. So it's not something that where you can ignore it, especially in a battery bank, because there is a feedback loop, and this feedback loop can run away and you can have literal fire under your ass. So it is something that is must for long-term use. Defining long-term here is basically you really want to do something with it. It's not just a prototype. Like for people, prototype sometimes they do try it, but most of the time it's like no, you have to put BMS, and it makes if you're not having that, battery packs become unstable because they could literally combust on fire. So it's not something you can have as a safe alternative. Now, how do we do that? Well, first we start with topology optimization. I specified there is only two way of connecting a cell, either serial or parallel. Now, parallel generally is chosen for many small loads like your battery bank. The reason for that, parallel cells auto balance. So you have like this. There are many power banks. If you open them up, you will find exactly like this. The reason for that, yes, this has the side effect of lower voltage, and if you want speed charging, that means you have to have a circuit that can take, let's say, 3 volts and boost it up to, let's say, 20 volts in case of a power delivery standard. Expensive equipment, but can be done. Benefit of this, the cells will auto balance. If you disconnect everything, basically you charged it up, you disconnect it, the cell that is degrading very quickly, basically losing charge quickly, the other cells, because they are directly connected, they will end up dumping their electricity into the one. So it discharges auto balancing. Every moment that is self discharging, it's self balancing also. So whenever you went to again to use it, it will always be perfectly balanced, as all things should be. So it's quite amazing for those kind of applications. However, some places you need high voltage, let's say for your laptop. So your laptop is not going to have like a DC to DC circuit which takes like 3 volts or 2 and 20 volt. That ampere wastage would be too high. So generally in those sort of scenario, we try for active system that can charge control it. So once the moment some cell that has lower capacity starts to reach its complete charge, we'll dump electricity from that. Now in olden days, we simply used to have resistors, which will just act as a heating element, as a load, and it will basically drain this slowly, and it will wait for other cells to catch up. So other cells are also fully charged. That was okay for small load, but not okay if you are talking about a car or a truck or a bus. That's not acceptable for that. So we started to use something known as active balancing. Basically, we drain this battery by dumping its electricity into other systems. So that way we have much more active, much more efficient use and less heat, instead of like, because you can easily imagine if your cells are huge, hundreds of amperes of cell, that dumping that few hundreds of watt, like you are talking about 100 kilowatt heating element that you have to handle. People don't want to do that. So we started to use active balancing cell, and this we also do it during discharge cycle. So one cell does not end up in a scenario where it's like, it reaches 2 voltage low and cuts off the system. So we have to do all this actively every time when you're charging, every time you're discharging. Now the way we do this, because again you can't see the cell in X-ray, it will not make any difference, we use voltage. Now this is the critical aspect. There are many popular chemistry that you can buy for lithium. Two of the primary one would be lithium ion and lithium polymer, and yes, they have inherently different chemistry, inherently different voltage parameters. So your battery management circuit either has to be smart enough to know which system is connected to, or it has to like be programmed in such a way like, bro, it's a lithium polymer cell, handle it this way. It's a lithium ion cell, let's say for a drill battery, it will like, bro, handle it this way. So you have to have something that handles cell voltage, because every chemistry has a different voltage. Let's say lithium ion has different, lithium titanate has different, lithium polymer has different, lithium iron phosphate has different. So all that reason you have to program that into your system. Otherwise voltage management would be off, and that's why every battery manufacturer that is like a reputable, and if they are selling battery management system, they'll say, hey, do not use this with the lithium polymer, do not use this with the lithium titanate. It's not meant for that. So what is the logic behind it? Well, in the early days I specified it, we started very dumb, but right now we have to have logic on top of logic, because we are trying to connect hundreds of this, thousands of this, and in some scenarios where you are talking about like giant power banks, that could go ludicrous level where you are talking about 10 megawatt of energy. So logic has to upgrade on a completely different level. So in the early days, as in like around 2015 and things like that, it was just like check the voltage. Now it's like check the profile of the cell. What does that mean? That means you check the temperature, that means you check the log of what happened before it. So if there was a very huge current draw, the voltage will sag, basically voltage will go down, but it will start to come back up over time. So you will wait for it, you will not freak out, hey bro, that cell went too low. You'll like, dude, I know if there was a spike, like let's say you pressed accelerator very quickly, it's like YOLO happened, and then you're like, okay, battery management is like, bro, I'm not gonna panic. Yeah, see, voltage starting to come back up. So you have to have these logic programmed into it. It's not as simple as like just check the voltage, if low, put more. That's not how it works. You have to calibrate for that, and programming is needed. That's why there are like, you can buy Chinese structures like this and it will be quite cheap, but they do not like, if you are very perfect, it's awesome, but any misalignment, they do not have any ability to fine tune itself. So it's like, it's a one size that fits all. It does not work very well for car kind of application. So you need different system for different chemistries, and many methods are used. So right now the most common practice that you will notice is that people generally make a lot of small cell connect as a parallel acting as a big cell, those big cell acting as a serial into one battery box. That box, multiple of those will be added to make a car battery bank. That's how it's done in Tesla. Now, why do we do with that many hassle? It has the easiest way to manage, because you will have a management that handles the sub managers, and the sub managers will manage the final cells. And each cells, because majority of the cells are connected in parallel, the total count of cell is very low. It can be managed, handled quite easily, quite effectively. So each of the methods have their own pros and cons, and you can easily go too deep into it and get a PhD into this. And there are generally few things you will hear, like top balancing, bottom balancing. Basically, when do you cut off? Do you cut off when something is overcharging, or when something is undercharging? Each of them have a benefit. Ideally, you want to have a cell that does not drift that much apart. If it's very close to each other, you will not notice anything. If it's very far apart, let's say, like this is a very good example. You have cells that are like 4.17, 4.17, 4.17, 4.17, 4.17, 4.19. It's bad. The cell is overcharged. 4.17, everything is cool. 4.193, that's overcharged. So you have to dump electricity of those things or cut off the charger. So these will be classified as top charging, balancing. So you will make sure the overcharging is happening because all of the cell are fully charged. Again, people choose different thing for different reason. If your things are more likely to go boom, you will be like, yeah, I can deal with undercharged battery, not with overcharged battery. But if your chemistry is like suitable of handling, low amounts of current, you will be like, okay, I'll deal with the overcurrent side. So these are the logic behind it. Like, it's not simple as just manage the voltage. You have to think about it, plus and minus, and you have to think in time also. It's like, yeah, the power drain is very critical. And on top of that, if temperature is too high, you have to be like, okay, I'm not gonna try to balance it because the temperature is too high. I will just damage it more. So what we can expect in the future? Well, we have to use better algorithms. Now, thankfully, the algorithms that are deployed right now, they are quite good, because the cars that were made as early as 2004 and 5, they are still not returned. Basically, most of the car batteries that you are seeing in the open market, they are generally coming from what we call as basically accidents, crash, runoffs and all that jazz. They are rarely coming because the cells are useless. That has not happened yet, because the cell management system we put overbuilt. Basically, we went YOLO on that. We had to. It's like, if imagine you are a company, you are selling some super expensive car and it stops working midway, you will like, yeah bro, that's unacceptable. So we need to fine tune our algorithm, and we have to improve the efficiency, because again, we have learned a lot and we stopped doing register dumps. Now we're like taking the electricity and dumping it to somewhere else, but we have to become a bit more efficient with that. Now, topology is a very interesting aspect. As you can see, this is like a one battery box of a battery pack of Tesla. So you can see all these large plate. These large plate is single cell. This is one cell, this is second cell, this is third cell. So this will be classified as 3C. 3S, I'm saying, sorry about that. Now, the reason for this is basically the main computer will only think about, okay, there is 3 cells I have to manage in this box, and there will be 7 to 18 box. So it's not too overwhelming. Now, benefit of this, each of the cell is connected with a very thin wire. The reason for that, those are de facto fuse. So if something overcurrents happens, those will break. And because so many are connected in parallel, one or two breaking will not even affect it at all. Like, computer will have hard time detecting, I think one cell is just down. That will not happen. So it is very good and resistance against, like, few cells going in each box without ever noticing. Like, you can literally drive for 10 years and you will not even notice, hey, I think one of the cell is broken. That will not have any issue. So topology wise, it has benefits. It has the benefit that you can have cooling jacket in each of the cell. Side effect is very space inefficient. You want to have big cells. Bigger cells gives you bigger life, but side effect, thermal management becomes an issue. And cost also, because these cells are mass produced, so the cost is too low. But when you compare to like how Volt Electronics tried to did that, Chevrolet Volt did that, the cells were awesome. They were huge, but they were expensive as hell because they were not mass produced. So again, each topology has its own pros and cons. And final benefit of this modern era, data logging. Because the more data you collect over time, not just like, okay, I have tested this car for 1 month and like that's the data. No, I'm talking like over years. If you notice a trend, let's say every summer you are noticing the voltage sag is not acting up, so you will know that, okay, summer equals no voltage sag. Fine tune my algorithm for that. In winter you'll like, okay, voltage sag is different. Or sometimes you're like, hey, charging current is completely different, or internal temperature is too high, or the dendrite production is very high in winter. So you're like, bro, it's winter outside, let's chill. To find that kind of data, you need data logging. Thankfully, memory cards are even like 16 Gigabyte memory cards are very cheap. You can, like, if you are building a battery box, you can build it out of Raspberry Pi. Not even Raspberry Pi, let's come down, even Arduino. You can have Arduino and you can monitor voltage of all of these and create an Excel sheet of, like, a few megabytes, and that will be like storing data for months and months. So we can do that. Like, all these we can do. We are fine tuning our technology, fine tuning our resources, and there are a lot of people that are building battery banks on their own. So all this knowledge, information is really helping everybody. It's not just like corporation, it's also helping the little guy, so to say. So this was my presentation on battery management system. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friend. That will help me a lot. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me extra disappointment, and please leave a comment because I like to reply to all of them. And subscribe, press the bell icon if you're free. And as always, thanks for watching.